When you think of electricity, what's the first thing that comes to mind? Probably a wire. We're used to thinking of metals as the best way to conduct electric current. And it's true, metals are found in pretty much all the electronics that we use, in light bulbs, phones, computers, TVs, and countless other appliances. But believe it or not, there are certain non-metals, such as conductive plastics, that can act as conductors too. Their special properties challenge our assumptions about non-metals. This is because the electrons of metals are delocalized, meaning that the outermost electrons in a metal atom are held loosely, allowing them to flow more freely. In contrast, the outer electrons in the atoms of a non-metal are held more closely to the nucleus, preventing movement. Think about an electrical wire. Inside, the charges flow easily through the metal filaments. On the outside, the rubber coating keeps these charges from flowing into our bodies and electrocuting us. Conducting polymers refers to polymers that can transmit electrical charge, rendering them viable conductor options. These substances integrate metals' electric charge conduction capabilities with the benefits of polymeric capability. One of the most example of conducting polymers is the polyaniline. What is polyaniline? Polyaniline is a conducting polymer. Polyaniline is known for its simplicity, environmental stability, and ability to be doped by protonic acids. Polyaniline is found in one of the three idealized oxidation states during the polymerization of aniline monomer: leucoemeraldine, white clear, emeraldine, salt green, base blue, and pernigraniline, blue violet. This conducting polymer can be synthesis chemically and electrochemically methods. These three oxidation states of polyaniline have their own differences. Fully oxidized polyaniline is known as pernigraniline base. Half of the oxidized polyaniline is reduced as the emerald base, and polyaniline is completely reduced as the leucoemeraldine base. Among these, emeraldine is the most stable and conductive, with a conductivity in the range of 10s per centimeter, while its salt form has a conductivity of 30s per centimeter. The exact conductivity of polyaniline depends on the synthesis method, and it can be controlled by submerging the emeraldine base in an aqueous acidic solution. The emeraldine base form of polyaniline is difficult to process because of the lack of solubility, and it is obtained as a dark powder. In addition, polyaniline is a p-type semiconductor which has a band gap of 2.8 to 3.2 eV. This conducting polymer has potential applications in various fields, such as organic electronics, biomedical fields, and anti-corrosion materials due to its extraordinary properties, such as exceptional electrical features, decent chemical and environmental stability, low cost, and easy preparation process. To give a background about the semiconductor, a semiconductor is a material that falls between conductors, materials that allow the flow of electric current, and insulators, materials that do not allow electric current to pass. Semiconductors have unique electrical properties that makes them essential components in modern electronics and technology. Semiconductors have an intermediate level of electrical conductivity, which can be altered or controlled by factors like temperature, voltage, or the addition of impurities, doping. Semiconductors have a band gap, a range of energy levels between the valence band, where electrons are bound, and the conduction band, where electrons can move freely. Electrons in the valence band need a specific amount of energy to jump to the conduction band, allowing for controlled flow of current. Doping, adding small amounts of impurities dopants to a semiconductor, can significantly affect its electrical behavior. Two common types of doping are N-type, adding extra electrons, and P-type, creating electron holes. Semiconductors are crucial components in electronic devices such as transistors, diodes, integrated circuits, and solar cells. The ability to control the flow of electrons in semiconductors forms the basis for digital logic, allowing for binary operations that underpin modern computing. Moreover, a p-type semiconductors are holes that are majority of carriers in. Electrons are minority carriers in a p-type semiconductor. In a p-type semiconductor, the hole density is much greater than the electron density. The acceptor energy level of the p-type is close to the valence bond and away from the conduction band. On the other hand, the n-type semiconductors are the majority of charge carriers in n-type semiconductors are electrons. Holes are minority carriers in a n-type semiconductor. In the n-type of semiconductor, the electron density is much greater than the hole density. The donor energy level of n-type is close to the conduction band and away from the valency band. An example of n-type semiconductors is the gallium phosphide. A phosphide of gallium is a compound semiconductor material with an indirect band gap of 2.24 eV at room temperature. This semiconductor has been used in the manufacture of low-cost red and green light-emitting diodes, LEDs, with low to medium brightness since the 1960s.